Welcome in. All right, so the electromagnetic spectrum. So I just want to be able to introduce now that hopefully you understand how the EM, so the electromagnetic wave, kind of is generated and propagates. We'll talk about that a little bit more in this video, and I have done the video, so I'll put up a link up above there where the simulation that you're looking at actually comes from. So the simulation here that you see on the screen is a propagation of just one single wave. But of course, the waves are radiating out. So hence, the radiation word that we use, where basically the amount of energy which is stored within the wave starts to propagate and radiates outward, okay, as it continues on. Now, if you single in and you hone in on one wave in particular, it's going to look something like this, where you have basically every single wave, which is an EM wave, is composed of two components that we can't normally visually see, although we can see some of them, like the visual spectrum. Now, that wave is generated into those two components of the electric field and magnetic field, which are continuously changing and then propagating all the way through until they get either absorbed or it changes into some other form of energy. So that's how these waves look like. So take a look. You can take a peek at that video to see how exactly the explanation is, so that you can understand these EM waves and how they get generated and then get propagated. Now, in our goal here in this video is we want to be able to now hone in on the spectrum of these EM waves that we have. So now you should know that the waves are propagating at a particular speed. So we notice this is basically in nature. So this is what we observe. And that particular speed is approximately, so I have it in here exactly, and then approximately at 3 × 10⁸ meters per second. So it's really, really fast. If you are more familiar with, for example, at least intuitively, kilometers an hour, well, that's 1.08 billion kilometers an hour, okay? Or if you're more intuitively thinking of miles per hour, well, that's approximately 670 million miles per hour. So it's really, really quick. Now, what is it that is so quick? It's a wave. And now every single wave is basically broken down into two of its components that you have that we can measure it out. So this C, this speed of light, which is really the speed of the wave, which is the electromagnetic wave, but we just got so used to calling it light. It's not just light. There are hence the spectrum, right, that we have, the visible light that we see, is actually a very tiny part of that spectrum. But these EM waves are coming in from numerous wavelengths and numerous frequencies. And every single one of them does indeed propagate at this speed, but the actual wavelength that it has and the frequencies that it carries is different. And that's what gives it its characteristics and then utilization. So we use them for all kinds of wonderful things, okay, in terms of trying to see this. And now, based on these two components, we can now talk about the different spectrum that we have. Now, here is kind of a summary of these spectrums, okay, that we normally see within here. So here is a table that has been created, okay, so within here. And the first item, which is the radio wave. So you have this spectrum, and again, notice I have put in, so both frequency and the wavelength. And remember, when you multiply these two together, it's going to give you the speed of the propagation, okay, for all electromagnetic waves. But they do change in frequencies and wavelengths, okay, that you have. So now this frequency and this wavelength, okay, for instance, what we utilize for radio waves, so this is anything to do mostly with communication side. So it has radios. So if you're thinking about the AM radio, okay, the FM radios, you have TV broadcasting, okay, that you have You have networks that are carried out, okay? So they're all along this particular spectrum. And notice that the frequency is 10 to the 3 all the way up to about 10 to the 9. And that varies because it will depend which textbook you're reading, which research you're looking at, right? So that will vary. So don't hold it exactly, you know, oh, it's only in between these two ranges. No, you know, it can carry over, and then there's some overlap, okay, that you have happening. And this within here is definitely, so all the antennas that you see, you know, cell phones, okay, etc., okay, be mindful that the radio waves, okay, we call them radio waves, right? And we don't, you know, someone says radio, we think, oh my gosh, you know, here's a radio. No, it's not necessarily radio, okay? We've just called them that way. And again, it comes kind of from that radiation, right? So the radiation of the waves that you have that are carried out, okay, throughout. So the next one, typically, as we're moving along the spectrum, so the ones that are a little bit bigger than this, okay, and now a little bit, now this is already pretty quick, but 10 to the 9 to approximately 10 to the 12 hertz, right, which is monstrous, so that gets into the billions, okay, and trillions, okay, or if you're thinking about prefixes, that gets you into the giga, right, and tera kind of a range. Those are kind of typically microwaves. And then microwaves, well, you probably have heard of a microwave itself, okay, so here's some applications. So microwaves, you know, radars, okay, you have satellite communications. They can certainly heat up the food that we have by making the water molecules vibrate. So you have these microwaves that are in that spectrum next. So it just kind of moves along. But notice, as the frequency increases, the wavelength decreases. And that should make sense because, again, if you're going back to the equation, right, if one of them increases, the other one will decrease. They're inversely proportional to each other. Wavelength and frequency, that is. Okay, so be mindful of it, and that's exactly what you're going to see. You're going to see an increase in this way, and then a decrease, okay, as you're going along in this way. So then, you know, you have the typical one, which is infrared. So that infrared, notice that it now starts to get into pretty quick, okay, 10 to the 12, 10 to the 14 range, so kind of beyond the tera, and that is with regards to your prefixes. And then these, okay, wavelengths just keep coming down. You know, they get smaller and smaller and smaller. Okay, so infrared is, you know, very often felt in heat. Okay, so in various thermal imaging that you have. We certainly also use it in our remote controls. Okay, you know, so you see that signal being sent out there. Some in astronomy, okay, within. Now, we don't normally see these infrared, okay, so it's not something that is visible to us. That will be the next item. And this next item, notice how tiny it is, but it's so important to us. And that is the visible light, right? So visible light is actually in the 10 to the 14 range. And notice that it ranges within this little tiny spectrum. And notice that the wavelengths are around 10 to the negative 7. Now, very often you'll see these wavelengths not given in scientific notation, but they will be given in prefixes, and they're typically in nanometers. Nano, if you remember, is 10 to the negative 9, right? So now you're looking at this and you might say, well, you know, so this is 10 to the negative 7 in here, okay? Why to the 9? Well, because the way that we typically will write these out as we're going through, I'm going to just show you because there's nice images, and I'll put all the links to the references down below. Okay, so this one I just grabbed. You can honestly search engine anything, you know, so I just like this one, and you will notice that it has, okay, so the spectrum, these are the visible colors that we have, so from red, orange, you know, yellow, green, bluish, violet, etc. And then notice that there's a wavelength in nanometers, so, you know, it starts from 740 nanometers, so that would have been 740 times 10 to the negative 9. And of course, if you put it in scientific notation, then it would move a couple decimal places, and it would have been 7.4 times 10 to the negative 7. And then that spectrum is carried out. So you have all of these wonderful colors, and our brain is able to sense this, okay, so through our eyes, and then pick up and distinguish the different wavelengths, okay, and frequencies that we have, okay, and then we just register, so our brains, and we see these colors. if we're lucky enough to be able to see. So that's what you have. So these are literally just EM waves, and they're just propagating, and they have a very tiny kind of a spectrum within here, so between the 740 to 380, so that's the wavelength. So the wavelengths get shorter, but that means the frequencies get faster, right? So if I go back into the table, okay, within here, so let it load. So there you have it. Okay, so here is our next ultraviolet. Okay, so those are the UV rays. This is kind of where we're kind of generating our vitamin D, but we can of course get sunburned. Okay, from that. It is also used in various sterilizations, disinfections. You have the UV light. Okay, so you have in here. Sometimes you hear about black lights. Okay, so those are all kind of the components that we have under this spectrum. Notice the spectrum is from 10 to the 14 to 10 to the 17. So, these are really fast, which means that the wavelengths just start to plummet, right? So this is kind of past the visible light spectrum, and now it gets, and then the wavelength just gets shorter and shorter and shorter. The one that you see next, which is X-rays, so those ones very commonly people will hear about. Okay, so these X-rays are used heavily in medical imaging from X-rays. Maybe you've heard of CT scans. Okay, so those are kind of the computerized tomography. Those are just much more detailed, and they give you kind of in slices. Okay, instead of X-ray, which gives you just one particular image. Okay, CT scans give you a more in-depth image where there's some depth into it. Okay, within here. I won't go into detail into that, but I just want to be able to mention that those are also using X-rays. Now, the unfortunate thing is that X-rays do penetrate through most of the materials, and they can cause cancer, of course, depending on how high of a dosage you have, so how much radiation you've been exposed to. And here, when we say radiation, it just means how much energy is being carried out within these X-rays, and then they're penetrating through your organs, bones, etc. And then the next one after that, so these are kind of the most common ones, from radio waves, microwaves, infrared, visible light spectrum, ultraviolet, the UV one, X-rays, a lot of people are very familiar with those, and then gamma rays, which is kind of one of the last ones that we talk about, which is kind of 10 to the 20 hertz, which is enormous. And then the within here, so as you can see here, is 10 to the negative 12. So this gets into kind of the pico range of the prefixes, so nano, pico, which is 10 to the negative 12. And those are very, very short wavelengths, within here. Now, these ones are produced by radioactive atoms. So sometimes if you're thinking about, if you have an electron, so within here, so those are on the subatomic sometimes level, the nuclear level. As you're going to be studying, you're going to be talking about gamma rays, which are kind of released, and it is pretty radioactive, that you have, and it carries in definitely a bit of energy, within here. And again, this can also penetrate through and indeed can damage living cells. So here is the spectrum as a whole, and you will have this spectrum. You're going to be, these are kind of, there's probably about 7 of these that are the key top items within the spectrum. And then keep in mind that when you take their frequency and you take their wavelength, you multiply them together, then you get the propagation, the speed of this EM waves and how it propagates. And it's the same for all of these. So within here. Now here's another table in terms of the red, orange, yellow. So this is more in the visible spectrum. So here's a little bit of a summary, within here that you have right there. And I can certainly add in, so I'll put it in the description. You can download these tables for yourself if you want to, and then use them as you please. To be honest, I'm just hopeful that you find this useful. So you have your frequency ranges and then the wavelength ranges. So this is exactly what you've seen. So notice the reds, the orange, the yellow, the green, the blue, kind of indigo violet. So all of these that you have there. So now to kind of summarize this and then complete with a few items that you should know. So this kind of comes in. So I wanted to be able to do and talk about just a couple of more items within here. So the first thing is Very often you hear, EM waves and then EM and the word radiation. And you might be thinking, well, what exactly is the difference in here? So waves themselves, we have sound waves, right? We have all kinds of mechanical waves. Now keep in mind, EM waves are transverse waves, right? So that's where the field itself is actually changing perpendicularly to the propagation of it. But wave in general is just describing, the process of an energy which is being transferred along, is something that we have described as a wave. Now the radiation, so when you say EM radiation, it talks about the fact that you have an object which starts to generate these waves, and then they propagate out radially out, and then they span out all over as they're propagating, so they're radiating out. And in that radiation, you can assume, that they are carrying, so it's the waves that are carrying the energy within. So it is describing the whole process, of these waves propagating and also containing the energy that they have within them, and then they're processing it back and then they're expanding out. Now, there are three key mechanisms for the generation. So the video that I've done before, I kind of concentrated on the accelerated charges, which indeed is the case. So you do need the accelerated charges, so the two below. Definitely still talk about that, but I just wanted to mention and let you know what the difference is. So you can generate EM waves and EM radiation, right? So radiation, again, think energy being propagated out and radially expanding. So by charges that are accelerating, right? Now those are typically organized in some way, and then they will be continuous, right? So they're just continuously passing along. Now the next one, which is thermal kind of agitation, which is really the black body radiation. So because you have, as soon as you start, so thermal, so when you start to have the thermal energy, and for instance, the temperature keeps increasing, so you'll note that materials in general will start to vibrate. Now, when they're going to vibrate, they can give off, this energy as a whole. We radiate energy, because we're at a certain temperature. And because of that, we can actually radiate. You can take an infrared sensor, which will actually sense heat around us. You'll see sometimes these visions, kind of the red is around, a body, because it is radiating, this energy throughout. So these random movements, will continuously give off various radiations that you have. And so you sometimes call it thermal agitation or black body radiation. Black body, we typically don't necessarily, we might not see it with our eyes, that we have. And then the last one is through kind of quantum transitions, and those are electrons, that are, so if you may recall from chemistry, if your electrons, goes from an orbit and then it drops in orbit, so basically releases energy. That drop in energy, so that release, is converted into an EM wave, so sometimes called a photon. They are at random, but they're also discrete. So it's not like they are continuously being generated, right? So if the electron drops in, it will give off that energy, and it's discrete. It happens, and then maybe another electron, and then another one happens. But it doesn't happen on a continuous basis, throughout, where it's just continuously releasing those EM waves. It will sporadically and discretely release them throughout. So accelerating charges, right? So thermal, so the movement, that you have, and those typically will happen in a random process. And then you have the electrons, which basically transition out from their orbits, or sometimes this is called quantum. And this is the three key mechanisms for generating these EM waves. Now, you will find this, I actually found a really good resource. So it's from the OpenStax, so you can easily access it. I'll put up a link in the description. This is from the college physics textbook on chapter 24.3, and it has and talks about the spectrum in much more detail than I talk about in this video. Now they bring about three key kind of rules to remember. So if you take the spectrum, so all the way from radio okay, and then all the way to gamma, okay, and then everything in between from X-rays to UV, etc. So if you take that spectrum, okay, so there's three things that you should kind of think about that happens. And those three items, okay, so the first one right here, one of the rules is that if you have a high frequency, right, so higher frequency EM waves will have a higher energy and a higher penetration, okay, ability than lower ones. So if you look at here, so these ones, okay, so within, so the higher frequency, so this, you're going in higher frequencies in this direction. So what that means is that these, okay, will have a higher potential for penetrating through materials. Now this is also because their wavelengths, okay, are very tiny, okay, that you have. And these, okay, will carry also more energy, okay, than these ones over here, okay, as you're going up above. So that's one of the first things. So higher frequencies, okay, higher energies that they carry, and then higher potential for penetration. So that's kind of rule number one. Rule number two, okay, which the text actually points out, is that higher frequencies can carry more information. Now this basically is like rule number one, because if you have more energy that it can carry, it can therefore carry more information per a certain amount of unit of time, okay, that you have, because there are higher frequencies that are carried throughout. Now this is again, so higher frequencies in comparison to the lower frequencies. So the, again, gamma rays in comparison to radio waves, okay, they can contain more information, and X-rays can contain more information than, for example, radio waves, okay, and the ones that are on the lower frequency range. And then the last one, so shorter wavelengths. This is still on the higher frequency side, because if you're going to have a shorter wavelength, that means you have a higher frequency, okay? Then what these, and this is the reason why we use, for example, X-rays, okay, that we have. So these have a higher resolution ability. So they can penetrate, right? And then they can provide you better resolution images because their wavelengths are shorter. If the wavelengths are too long, then they won't capture, okay, the transitions and changes in between, so as they're going through. So again, shorter wavelengths, okay, so the shorter the wavelength, okay, then the higher the resolution that it can provide you. And this is through the images. So that's the reason why we use X-rays. Don't really typically want to use gamma rays because they're very radioactive, okay, so they're not, I mean, X-rays are already not the greatest for us, okay, but at least we can tolerate it in certain amounts, okay, less risk than definitely gamma rays. All right, so that is the spectrum. So this particular spectrum you should be familiar with, and now you should also take out and remember that all of these waves, okay, EM waves, are traveling exactly at the same speed, which is crazy, and they just simply have a different wavelength and different frequency throughout. And if you study electricity and magnetism and learn about electric fields and magnetic fields, then you can understand EM waves. Thanks for watching. All right, we'll see you in a future video. Bye, everybody.